Welcome to AWS Transit Gateway Connect. Welcome everyone. Today we're diving deep into AWS Transit Gateway Connect, one of the most powerful networking solutions for hybrid cloud connectivity. This presentation will take you from business justification all the way through hands-on implementation. We'll cover real-world use cases, detailed technical architecture, and complete step-by-step deployment. Transit Gateway Connect is transforming how enterprises connect their on-premises networks to AWS, especially for SD-WAN deployments. Let's explore why this matters and how to implement it successfully. What is Transit Gateway Connect? Transit Gateway Connect is AWS's solution for high-performance, dynamic connectivity between on-premises networks and AWS using GRE tunnels and BGP routing. Think of it as a bridge that speaks the same language as your existing SD-WAN infrastructure. Instead of static VPN configurations, you get dynamic routing that automatically learns and propagates routes. The key differentiator is performance, up to 5 gigabits per second per connection compared to 1.25 gigabits per second for site-to-site VPN. Plus, you can scale with multiple connections for even higher bandwidth. Why Transit Gateway Connect matters. Let me share a real scenario. Imagine you're a manufacturing company with 50 factories worldwide, each with IoT sensors sending data to AWS for real-time analytics. Traditional VPNs often create bottlenecks and add significant management complexity. With Transit Gateway Connect, your existing SD-WAN can dynamically learn AWS routes, automatically failover between paths, and scale bandwidth as needed. It's like having your on-premises network naturally extend into AWS. The business impact: faster time to market, reduced operational overhead, and the ability to burst compute workloads to the cloud seamlessly. Real-world use cases. Let's look at specific scenarios where Transit Gateway Connect shines. First, SD-WAN integration. Companies using Cisco, VMware, or Fortinet SD-WAN can extend their fabric directly into AWS without architectural changes. Second, high-performance applications like trading systems that need sub-millisecond improvements over traditional VPNs. Third, IoT and manufacturing, where you're moving massive amounts of sensor data to AWS for analytics. I've seen financial services companies reduce their AWS connectivity latency by 40% just by switching from site-to-site VPN to Transit Gateway Connect. The performance gains are measurable and immediate. Technical architecture overview. Now let's understand how this actually works under the hood. Transit Gateway Connect sits on top of your existing VPC attachments and creates GRE tunnels to your on-premises equipment. The beauty is in the layering. Your physical connectivity stays the same, but now you get dynamic BGP routing instead of static routes. Each connect peer can handle up to 5 gigabits per second, and you can create multiple peers for redundancy and additional bandwidth. The architecture is designed for enterprise scale, multiple VPCs, multiple on-premises sites, all connected through a single transit gateway with intelligent routing. GRE tunnels explained. GRE tunnels are the transport mechanism that makes this magic happen. Think of GRE as an envelope. Your original packet gets wrapped in a GRE header, sent over the internet, then unwrapped at the destination. What's clever about AWS's implementation is they handle all the complex stuff: tunnel endpoint management, encryption capabilities, and high availability. You just configure your side to point to AWS-provided IP addresses. The tunnel uses link local addressing, 169.254xx, for the BGP peering, which keeps it separate from your production networks. MTU is set to 1436 to account for the GRE overhead without fragmentation. BGP routing deep dive. BGP makes the magic happen. It's the protocol that automatically exchanges routing information between your network and AWS. Unlike static VPNs, where you manually configure every route, BGP learns and propagates routes dynamically. AWS uses ASN 64512 by default, and you'll peer with this from your on-premises router. The beauty is automatic failover. If one path goes down, BGP converges to alternate paths within 30 to 60 seconds. You can also implement advanced routing policies using BGP communities, local preference, and AS path prepending for fine-grained traffic control. This gives you the same level of control you'd have with enterprise WAN routing. Solution comparison. Let me walk you through when to choose Transit Gateway Connect versus other AWS networking options. If you need dynamic routing and have existing SD-WAN, Connect is usually the right choice. Site-to-site VPN is simpler but limited to 1.25 gigabits per second and static routing. Direct Connect gives you the highest bandwidth but requires physical circuits and weeks of lead time. The sweet spot for Connect is when you need more than VPN performance but don't want the complexity and cost of Direct Connect. It's perfect for cloud-first companies that need enterprise-grade connectivity. Traffic flow analysis. Understanding traffic flow is crucial for troubleshooting and optimization. When a packet leaves your on-premises network destined for AWS, it goes through several transformations. First, your BGP router does a route lookup and determines the packet should go through the GRE tunnel. Then the original packet gets encapsulated with GRE headers, creating an outer packet that travels over the internet. At AWS, the Connect peer receives the GRE packet, validates it, decapsulates the inner packet, and forwards it through the transit gateway to the destination VPC. The return path works in reverse, maintaining session affinity. Redundancy and load balancing. High availability is built into the design through multiple Connect peers and ECMP load balancing. Each peer creates an independent path to AWS, so if one fails, traffic automatically moves to healthy peers. Load balancing uses flow-based hashing, where source IP, destination IP, and port numbers determine which path a flow takes. This ensures packets in the same conversation stay on the same path, preventing reordering. In practice, I recommend at least 2 Connect peers for production workloads. The failover time is typically 30 to 60 seconds, depending on your BGP timer configuration. Step 1. Create Transit Gateway. Now let's get hands-on with the implementation. The first step is creating your Transit Gateway, which becomes the central hub for all your connectivity. The key parameter here is the Amazon side ASN 64512 is the default, but you can choose any private ASN that doesn't conflict with your on-premises network. Make sure to enable auto-accept for shared attachments if you're in a multi-account setup. This command also sets up the default route table with automatic association and propagation. In production, you might want more granular control and disable these defaults. Step 2. Create VPC attachment. The VPC attachment is what connects your VPC to the transit gateway. You need to specify subnets in different availability zones for high availability. Choose private subnets dedicated to transit gateway attachments. These subnets won't host any EC2 instances, they're just for the network infrastructure. The subnet selection affects which AZs your Connect attachment will use. Make sure your route tables are configured to send traffic destined for on-premises networks toward the transit gateway attachment. Step 3. Create Connect attachment. The Connect attachment is the foundation for your GRE tunnels. It uses the VPC attachment as its transport mechanism. Think of it as a logical overlay on top of the physical VPC attachment. This attachment inherits the availability zone placement from the underlying VPC attachment, which is why we needed subnets in multiple AZs in the previous step. Once this attachment is created and shows as available, you can start creating Connect peers that will establish the actual GRE tunnels. Step 4. Create Connect peers. Connect peers are the point where the actual GRE tunnels and BGP sessions are created. Each peer requires a unique /30 subnet from the 169.254.0.0/16 range. The transit gateway address is the AWS side of the BGP peering, and peer address is your on-premises side. Ensure these do not conflict with any existing network addressing in your environment. The peer ASN should match your on-premises BGP router configuration. AWS will provide you with outer IP addresses that your GRE tunnels will connect to. Getting Connect peer details. After creating your Connect peers, you need to retrieve the AWS-assigned outer IP addresses. These are the public IPs that your on-premises GRE tunnels will connect to. The Connect Peer Router IP address field in the response is critical. This is what you'll configure as the tunnel destination on your on-premises equipment. Save these addresses as they're needed for the next configuration steps. Also, verify that the BGP status shows the configuration is ready. The status will be down until you complete the on-premises configuration. Now we shift to configuring your on-premises equipment. The exact syntax depends on your router platform, but the concepts are universal. GRE tunnels pointing to AWS endpoints, and BGP sessions over those tunnels. Key considerations include MTU sizing, BGP timers, and route filtering. I always recommend starting with aggressive BGP timers for faster convergence in cloud environments. Make sure your internet firewall allows GRE traffic, Protocol 47, to the AWS outer IP addresses. Some firewalls need specific configuration for GRE tunnel traffic. Cisco router configuration. Here's the complete Cisco configuration for both GRE tunnels and BGP. The tunnel source should be your internet-facing interface, and the destination is the AWS outer IP address we retrieved earlier. Pay attention to the MTU and TCP/MSS settings. 1436 for MTU and 1396 for TCP/MSS prevent fragmentation while accounting for GRE overhead. The Keep Alive settings help detect tunnel failures quickly. The BGP configuration uses the inside tunnel addresses for peering. Use aggressive timers, 10/30ths, for faster convergence compared to default BGP timers. BGP configuration deep dive. The BGP configuration is where the dynamic routing magic happens. You're establishing neighbor relationships with the AWS Connect peers using the inside tunnel IP addresses. The network statements advertise your local routes to AWS. Make sure you're only advertising the routes you want AWS to learn. Use route maps if you need more granular control. AWS will automatically advertise your VPC CIDR blocks to your on-premises router. You can verify this is working by checking Show IP BGP on your router once the sessions come up. Verification and troubleshooting. Verification is critical to ensure everything is working correctly. Start by checking that your BGP sessions are up and routes are being exchanged properly. Use the AWS CLI to verify Connect peer status and route propagation. On the router side, check tunnel status, BGP neighbor states, and routing table entries. Common issues include MTU problems, firewall blocking GRE traffic, BGP authentication mismatches, and IP address conflicts. The flowchart shows a systematic troubleshooting approach. Monitoring and performance. Once everything is running, ongoing monitoring is essential. It's important to monitor BGP session state, tunnel utilization, latency metrics, and route table changes. AWS CloudWatch provides metrics for Connect peer status and traffic volumes. On the router side, SNMP monitoring can track tunnel state and performance metrics. Set up alerts for BGP session state changes and implement automated failover testing to ensure your redundancy works as expected. Cost optimization strategies. Understanding the cost model helps optimize your deployment. You pay hourly for each Connect peer plus data transfer charges, similar to other AWS networking services. Cost optimization strategies include right-sizing the number of Connect peers based on bandwidth needs, using AWS Cost Explorer to monitor data transfer patterns, and considering regional optimization in multi-region deployments. Compare the total cost including operational overhead against direct connect for high bandwidth requirements. The break-even point varies by use case. Security best practices. Security is paramount when extending your network into AWS. Start with proper BGP authentication using MD5. Passwords, implement route filtering to prevent route leaks, and use VPC security groups for application layer protection. Monitor BGP sessions for unexpected route advertisements, and implement logging for all BGP session changes. Consider using AWS Transit Gateway Network Manager for centralized monitoring and alerting. Regular security reviews should include route table audits, firewall rule reviews, and verification that only authorized networks can establish BGP sessions. Advanced scenarios. Let's explore some advanced use cases that go beyond basic connectivity. Multi-region deployments where you connect the same on-premises site to multiple AWS regions for disaster recovery. Complex routing scenarios using BGP communities for path control, implementing QoS markings that survive the GRE encapsulation, and integrating with AWS Network Manager for centralized visibility. These scenarios require careful planning of IP addressing, BGP communities, and route filtering to prevent routing loops and ensure optimal path selection. Migration strategies. Moving from existing connectivity solutions to Transit Gateway Connect requires careful planning. I recommend a phased approach. Start with non-critical workloads, verify performance and stability, then migrate production traffic. You can run Transit Gateway Connect in parallel with existing site-to-site VPNs during migration, using BGP metrics to prefer the connect path while keeping VPN as backup. Key migration considerations include IP addressing changes, application testing with the new paths, and ensuring your monitoring tools work with the new architecture. Conclusion and next steps. We've covered Transit Gateway Connect from business justification through complete implementation. This solution transforms hybrid cloud connectivity by bringing enterprise-grade dynamic routing to AWS. The key benefits: higher performance than VPN, dynamic routing, integration with existing SD-WAN, and enterprise scalability make it ideal for modern hybrid cloud architectures. Your next steps should include piloting with a non-critical workload, measuring performance improvements, and planning your migration strategy. Start small, prove the value, then scale across your organization.